All right, in this video, we will be going over section 3.1. In this section, we'll be talking about mean value theorem. And of course, we will be going over some other theorems before we get to the mean value theorem. All right, I want to start with this definition 3.1, local extrema of a function. Okay, let's define what we mean by local extrema of a function. When we talk about local extremas, we have two local extrema. One, local maximum. The second one is local minimum. Okay, here is the definition of a local maximum. F has a local maximum at x is equal to c if there exists some delta greater than 0 such that f of c is greater than or equal to f of x for all x in this interval. For all x in the interval c minus delta comma c plus delta. This is the geometric representation of the interval c minus delta comma c plus delta. You have c in the middle. You measure delta this way, you get c minus delta, and then you measure delta to the right, you get c plus delta. This is the interval c minus delta comma c plus delta. Okay. If we can find such a delta, then we say that f has a local maximum at x is equal to c. Here is an example where you have a local maximum at x is equal to c. Suppose you have a graph of y is equal to f of x, which looks like this. Then we can see that according to this definition, we have a local maximum at x is equal to c. Why do we have local maximum at x is equal to c? That's because I can find a very small delta neighborhood around c. Okay, c minus delta and c plus delta. If I mark this, if I take a very small neighborhood like this is your c minus delta. This is your c plus delta. Then notice that if I pick any x value in this interval, then f of c is bigger than or equal to f of x, as long as you pick your x value in this interval. For example, suppose your x value is this one, then your y value would be this one. And that y value is f of x, because you pick your point x from here. Then this y value is f of x, and that f of x is less than or equal to f of c. That's what you want. Okay, as long as you pick your x value in this interval, your f of x is less than or equal to f of c. It's clear from this diagram. Okay, roughly speaking, maximum, you have a local maximum if you have a shape like this at the point x is equal to c, or you have a constant function like this. This is a constant function. This is the point c. Okay, this is of course the x-axis. Okay, roughly speaking, you have a local maximum if you have this shape, or if you have a constant function. All right, next, the definition of a local minimum. F has a local minimum at x is equal to c if there exists some delta greater than 0 such that f of c is less than or equal to f of x for all x in this neighborhood or in this interval. Okay, x is in c minus delta comma c plus delta. Okay, we have the reversed inequality here. You look at here. Okay, so here is an example where you have a local minimum at c. Let's say your graph of f of x looks like this, and here is the point c. Here I claim that at x is equal to c, I have a local minimum. Why is that? Because I can find a small enough neighborhood around c. Say this is the point c minus delta. And this is the point c plus minus delta. And this is the point c plus delta. Then if I pick any x value in this interval, my f of x is bigger than or equal to f of c. For example, if I pick my x value to be here, where x is here, then your f of x is this value. And that value is bigger than or equal to f of c. That's what we want. Okay, my f of x is bigger than or equal to f of c as long as I pick my x value in this delta neighborhood. Okay, so it is true here. So we have a local minimum at x is equal to c. Roughly speaking, local minimum means if your function looks like this locally, or if your function is a constant function, then you have a local minimum. At this point, you have a local minimum. This is your x-axis, by the way. And at this point also you have a local minimum. All right, so that's the idea of local minimum. That's the definition. The next thing I want to talk about is critical points of a function. Okay, when do we say that we have a critical point at a given point of a function? Here is the definition. A point x is equal to c in the domain of f is called a critical point of f if f prime of c is equal to 0 or f prime of c does not exist. Okay, a point x is equal to c is a critical point of f if f prime of c is equal to 0 or f prime of c does not exist. That's the second definition that we have in this section. All right, let's move on. The next thing I want to talk about is this theorem, theorem 3.3, local extrema are critical points. Okay, here is the statement of the theorem. If x is equal to c is the location of a local extremum of f, then x is equal to c is a critical point of f. Okay, notice that. What do you mean by local extremum? Local extremum means it's a local maximum or a local minimum. Okay, that's what we mean by local extremum. So again, the statement, if x is equal to c is the location of a local extremum of f, then x is equal to c is a critical point of f. Okay, that's what we need to prove. Let's prove this theorem. I want to prove this theorem for the case when we have a local maximum at x is equal to c. Okay, the proof for the case when we have a local minimum at x is equal to c is very similar to this proof. Okay, you can just modify this proof to get the proof for the case when we have a local minimum. So let's assume that this local extrema that this theorem talks about is a local maximum. Okay, let's assume that x is equal to c is the location of a local maximum of f. Here, to prove this theorem, so what do we want to prove? We want to prove that x is equal to c is a critical point of f. Okay, to prove this theorem, we consider two cases. Case 1, when f prime of c does not exist. Case 2, when f prime of c exists. Okay, if f prime of c does not exist, by definition of a critical point, x is equal to c is a critical point of f. Okay, and we are done. If you go back to the definition of a critical point, x is equal to c is a critical point if f prime of c is equal to 0 or f prime of c does not exist. So in this case, if f prime of c does not exist, in fact, x is equal to c is a critical point. So we are done. Okay. And here is the second case. If f prime of c exists, okay, let's assume that f prime of c exists, and let's try to show that x is equal to c is a critical point. Okay. And we know that x is equal to c, we are assuming that x is equal to c is the location of a local maximum. So by the definition of local maximum, we should be able to find some delta greater than 0 such that f of x minus f of c is less than or equal to 0 for all x between c minus delta and c plus delta. That is the definition of a local maximum. Of course, the definition says this inequality, but these two inequalities are same. Notice that these two inequalities are same. Okay, I have written this inequality in a little bit different way by moving this f of c to the left hand side. All right, if it is a local maximum, we should be able to find delta greater than 0 such that f of x minus f of c less than or equal to 0 for x between c minus delta and c plus delta. Now, what I'm going to do is I'm going to focus on the left half of this interval. This is the whole interval c minus delta comma c plus delta. Let me focus on this left half of the interval, c minus delta comma c. Okay, for x values in this interval, in the left half of the interval, I'm going to look at this quantity. What can you say about this quantity, f of x minus f of c divided by x minus c? Well, your top quantity is less than or equal to 0. Because I know that x is equal to c is the location of a local maximum. So we have this inequality. F of x minus f of c is less than or equal to 0. So my top is less than or equal to 0. What about my denominator or the bottom? This is strictly less than 0 because I'm picking my x in this interval. That means your x has to be less than this number. X is strictly less than this number. That means x minus c has to be negative. Your top is less than or equal to 0. Your bottom is less than 0. That means this whole quantity has to be greater than or equal to 0. Okay? And now what I'm going to do is I'm going to compute the limit of this quantity as x approaches to c from the left-hand side. I can talk about this limit because I restricted my x values to the left half of the interval, c minus delta comma c plus delta. So I can fairly consider this limit as x approaches to c from the left-hand side, f of x minus f of c divided by x minus c. But we know that this quantity is always greater than or equal to 0. That means this limit also should be greater than or equal to 0. If you take the limit, this sign should remain the same. Okay. Now, what is this? This should be something that you're familiar with. This is the definition of the left derivative at x is equal to c. That is f prime minus c. That means the left derivative at x is equal to c. Okay. Similarly, next I am going to focus on the right half of the interval. I'm restricting my x to c comma to the interval c comma c plus delta. In that case, again, let's look at this quantity. Okay. In that case, again, f of c minus f of x minus f of c is less than or equal to 0 because of this. But what about your bottom? What about your denominator? This time your denominator is positive because your x is in this interval, x is bigger than c. So x minus c is positive. This quantity is less than or equal to 0. Your denominator is positive. This quantity is less than or equal to 0. That means this whole thing has to be less than or equal to 0. Okay. Again, I'm going to consider this quantity and I'm going to take the limit of that quantity as x approaches to c from the positive side, from the right hand side. I can do that because I restricted my x to the right interval of this interval. Okay. So if I consider this limit value also should be less than or equal to 0 because this quantity is less than or equal to 0. If this quantity is less than or equal to 0, the limit value also should be less than or equal to 0. But look at this limit. What is this limit? By definition, this is the right derivative of f at x is equal to c, which is denoted by f prime plus c. Okay. Now, we know that, we assume that f prime of c exists, right? That means your left derivative and the right derivative should be equal. But notice that this requires your left derivative to be greater than or equal to 0. And this requires your right derivative to be less than or equal to 0. Okay. The only way that can happen, only way this can happen is both are equal to 0. Okay. We want the left derivative and the right derivative to be equal because f prime of c exists. But we know that your left derivative is greater than or equal to 0, your right derivative is less than or equal to 0. Okay. For this to happen, both should be equal to 0. Okay. Otherwise, they cannot be equal. All right. So now this implies that f prime of c is equal to 0 because your left derivative and right derivative both are equal to 0. That means your derivative also should be equal to 0. Okay. That means by definition, x is equal to c is a critical point of f. That completes the proof. Okay. By the way, this theorem proves that all local extrema of f are critical points, but the converse is not true. Okay, this theorem tells you that if you have a local extrema at x is equal to c, it is a critical point. But if you have a critical point, you cannot say that it is a local extrema. Okay, so let's provide a counterexample. Here I have put a remark. The converse is not true. Converse of this theorem is not true. Here is the counterexample that I want to show you. Okay. First of all, this example asks us to show that x is equal to 1 is a critical point of this function. Okay. So let's show that. To show that x is equal to c is a critical point, I'm going to find the derivative of the function first. F of x is equal to 3x squared minus 3x plus 3. This should be actually 6. Okay, 3x squared minus 6x plus 3. That's the derivative. Now, I'm going to plug in x is equal to 1 in my derivative function. F prime of 1 is equal to 3 times 1 squared minus 6 times 1 plus 3, which is equal to 0. What does that tell you? By the definition of a critical point, see, f prime of 1 is equal to 0. That tells you that x is equal to 1 is a critical point. X is equal to 1 is a critical point by definition. Okay. So that proves that x is equal to 1 is the location of a critical point. All right, next, what are we supposed to prove? Then use a graph to show that x is equal to 1 is not a local extremum of f. That means at x is equal to 1, we have to show that using a graph, of course, we don't have a local maximum or a local minimum. Okay, so if you, in fact, if you graph this function f of x, you will get a graph like this. This is y is equal to f of x. By the way, this is what you get. As you can see, at x is equal to 1, your tangent to your function f of x is horizontal. That means f prime of 1 is equal to 0, as we saw here. But the graph looks like this. As you can see, you don't have a local maximum or a local minimum there. Because if you have a local maximum, your graph should look like this, or it should be flat like this. If you have a local minimum, your graph should look like this locally, or it should be flat. We don't have any of those scenarios here. See, function is coming this and going back up. Okay. All right. So this is an example which shows that the converse of the theorem is not true. Okay, let's move on. Okay, next, I want to talk about the Rollers theorem. I want to go over the Rollers theorem. Here is the statement for the Rollers theorem. By the way, this is theorem 3.4. Here is the statement of the Rollers theorem. If f is continuous on the closed interval and differentiable on the open interval a comma b, and if f of a is equal to f of b is equal to 0, then there exists at least one c between a and b for which f prime of c is equal to 0. Okay, these two are very important. F is continuous on the closed interval a comma b and differentiable on the open interval a comma b, and f of a is equal to f of b is equal to 0, then there exists at least one c value between a and b for which f prime of c is equal to 0. Okay. All right, here is the geometry behind this theorem. Suppose you have a function with f of a is equal to 0 and f of b is equal to 0. This is your a, this is your b. This is the graph of y is equal to f of x. As you can see, suppose that this is a smooth curve without any sharp corners, and it is differentiable on the closed interval, and it is clearly continuous on the closed interval. It is differentiable on the open interval and continuous on the closed interval. Then the conclusion of the Roller's theorem is that we should be able to find the value c between a and b such that f prime of c is equal to 0. Is that possible here? Of course it is possible. What do you mean by f prime of c is equal to 0? That means we should be able to find a point at which the tangent is horizontal, right? That's what we mean by f prime of c is equal to 0. This is the slope of the tangent. What about if you draw a tangent here? If you draw a tangent for this point, as you can see, that tangent is horizontal. Now, if I take my c value to be here, this value to be my c value, f prime of c is 0, according to this graph. Okay, so that's the point C. This is your horizontal tangent. I'm going to take this value to be c, then clearly f prime of c is equal to 0. Okay, so that's a geometric illustration of this theorem. Next, I want to prove this theorem. Let's quickly prove the Rollers theorem. So let's assume the hypothesis hold. Suppose f is continuous on the closed interval a comma b and differentiable on the open interval a comma b with f of a is equal to f of b is equal to 0. Okay. And then by the extreme value theorem that we learned in section 1.4, f attains both a maximum and a minimum value on the interval a comma b, on the closed interval a comma b. If someone does not remember the extreme value theorem, I have copied the extreme value theorem here. Here is the statement of the extreme value theorem. If f is continuous on a closed interval a comma b, then there exist values uppercase m, which is the maximum, and the lowercase m in the interval a comma b, such that f of m is the maximum value of f of x on a comma b and f of m is the minimum value of f of x on a comma b. Okay. So by extreme value theorem, f attains both a maximum and a minimum value on the interval a comma b. Okay. Now I'm going to consider two cases. Okay. The case one is if my local maximum or local minimum occurs at a point x is equal to c in the interior of a and b. Interior of a and b means c is strictly between a and b. Then by definition of a local extrema, x is equal to c is a local extremum of f. Okay, if your local maximum or local minimum occurs at a point x is equal to c, which is interior, which is an interior point of this interval, then x is equal to c is a local extremum of f by definition. Okay, but we know that local extrema are critical points. Okay, so that means x is equal to c is a critical point. So there are two things that can happen. What are the two things? Either f prime of c does not exist or f prime of c is equal to 0. But we cannot say that f prime of c does not exist because we are given that my function is differentiable on the interval a comma b. So f prime of c exists. So the only possibility is that your f prime of c has to be 0. Okay. All right, that's the case one. Case one, that is when your maximum or minimum occurs in an interior point of this interval. Now case two, what if both extreme values occur at the endpoints? What if your maximum and the minimum both occur at endpoint? Okay, in that case, clearly your function should be 0, right? Because at endpoints, your function is 0. That means your maximum and the minimum is 0. So your function has to be constant everywhere. Okay. If your function is 0 everywhere, you will get a graph like this on the interval a comma b. This is a, this is b. You will get a graph like this, 0. Okay. What is the derivative now? F prime of x is 0 for all x in that interval. For all x in the interval a comma b. So f prime of x is 0 for all x in the interval a comma b. Okay, that means you have infinitely many c values. Okay, that goes with the hypothesis of conclusion of the Rollers theorem. So that completes the proof of Rollers theorem. Okay, let's move on. Okay, next I want to work on this example. Sketch graphs of three functions that fail to satisfy the hypothesis of Roller's theorem, for which conclusion of the Roller's theorem does not follow. Okay, here are the three examples I want to provide. I will go over one by one. Think about this example. As you can see, this part is good. F of a is equal to f of b is equal to 0. But the problem here is it is even continuous. It is continuous on the open interval a comma b, closed interval a comma b. Continuous on a comma b. But the problem is not differentiable at this point. It is not differentiable at this point. Why? You have a sharp corner here. When you have sharp corner at those points, your function is not differentiable. Okay. So as you can see, you cannot find a horizontal tangent to this graph, or you cannot find a point. No C in the interval a comma b, in the open interval a comma b, such that f prime of C is equal to 0. That means the conclusion of the Roller's theorem does not follow in this case. Why doesn't it follow? Because it is not differentiable in the open interval a comma b. Okay, clearly at this point it is not differentiable. You have a sharp corner. Okay, perhaps I'll write not differentiable here. Notice that this is not differentiable. On a comma b open interval. Okay, all right. Next example I want to look at is this one. As you can see again, the hypothesis of the Roller's theorem does not hold in this case because this function is not continuous. As you can see, f of b is equal to f of a is equal to f of b is equal to 0. That's not a problem. That's good. But f is not continuous on the interval, on the closed interval a comma b, because you have a removable discontinuity at this point. Okay. And what can you say about the conclusion of the Roller's theorem in this case? Clearly, the conclusion of the Roller's theorem does not follow, because if you want a horizontal tangent, the only possible candidate is here. Here is where you can draw a horizontal tangent to this graph, but at that point, your function has a discontinuity. That means your function is not differentiable at that point. Okay, it's not differentiable, so you cannot find the value C such that f prime of C is equal to 0. No C in the open interval a comma b such that f prime of C is equal to 0. Okay. All right. The next example I want to talk about is this one. As you can see again, this part is good. F of A is equal to f of B is equal to 0. That's not a problem. Clearly from the graph, they are 0, but we have a discontinuity at this point. At B, you have a removable discontinuity. F is not continuous on the closed interval a comma b. And clearly, the conclusion of the Roller's theorem does not follow. As you can see from the geometry of this graph, you cannot draw a horizontal tangent to anywhere on this graph. Okay, there is no horizontal tangent. That means there is no C between A and B such that f prime of C is equal to 0. Okay. All right, let's move on. Next, I want to work on this particular example. Given that f of x is equal to x cubed plus 3x plus 1, how many roots does f of x have? We need to determine how many roots would this function have. Let's do some calculations. Okay. Notice that if you calculate f of -1, you will get -3. You just plug in -1 in your function, you will get -3. And if you calculate f of 0, you will get 1. It's clear. You put 0 here, you get 1, right? Now notice that this y value is negative, this y value is positive. Okay. Now what does the intermediate value theorem tells you? What does the intermediate value theorem tell you? First of all, let's look at the intermediate value theorem. I have copied that down here. If f is continuous on a closed interval a comma b, then for any k strictly between f of a and f of b, there exists at least one c value between a and b, a comma b, between a and b, such that f of c is equal to k. Okay, so we can apply that here. This looks like your a, this looks like your b. Then this is, of course, your f of a. This value is, of course, your f of b. And notice that the zero, the value 0, is between f of a and f of b, because 0 is between -3 and 1, right? So that means by intermediate value theorem, I will write IVT for the intermediate value theorem. Okay, by intermediate value theorem, there exists a C between A and B. My A is -1, B is 0 in the open interval, such that f of C is equal to 0. 0 is the value between -3 and 1. 0 is clearly between -3 and 1. So I need to be able to find the value C between -1 and 0 such that f of C is equal to 0. Okay, so that means I have a 0 there. By the way, I will call this C1. That's okay with you. I'll call this C1. Okay, instead of C, I'll call it C1. Okay, so at least we found a 0 now. We found at least one 0. Okay, we have a 0 in this interval. Now, but the question asks us to determine how many zeros we will have for f of x. How do you determine how many zeros we have for f of x? Well, for that, I'm going to do some more observation here. Of course, it's a calculation. I'm going to find f prime of x, the derivative of f of x, which is 3x squared plus 3. As you can see, this term is greater than or equal to 0 because you have a square here. This term can never be negative. Okay, so this thing is greater than or equal to 0, but you have a positive number added to that. That means this whole thing has to be strictly greater than 0. With that observation, I am claiming that this is the only 0 that I can have for this function. How do I justify this? Well, if we have another 0 in addition to this one, let's obtain a contradiction. Okay, suppose that there is another 0. If there is another 0, say C2, then f of C2 is equal to 0, right? That's what we mean by 0. But notice that this is a polynomial. Remember, polynomials are differentiable and continuous everywhere. Okay, that's a fact you can use anywhere. Polynomials are differentiable and continuous everywhere. Okay, so now we have f of C2 is equal to 0 and f of C1 is equal to 0. So my function, since polynomials are continuous and differentiable everywhere, f is continuous on C1, C2 closed interval and differentiable on C1, C2 open interval. That means all the hypotheses for Roller's theorem are satisfied. See, f of C1 is equal to 0, f of C2 is equal to 0. My function is continuous on the closed interval C1, C2, and it is differentiable on the open interval C1, C2. So I can apply the Roller's theorem. By the way, here when I write C1, C2, I'm assuming that C2 is bigger than C1, okay? But if it is not, you can switch these two numbers always. You write instead of C1, C2, you write C2, C1. And then you keep up with the proof. Okay, let's assume that C2 is bigger than C1 without loss of generality. Okay, now I can apply the Roller's theorem. F of C1 is 0, f of C2 is 0. Function is differentiable on the closed interval C1, C2. Function is continuous on the closed interval C1, C2, and it is differentiable on the open interval. So by Roller's theorem, there exists C between C1, C2. Between C1, C2, such that f prime of C is equal to 0 by Rolle's theorem. But is this possible? Can you f prime of C be equal to 0? It's clearly not possible because of this. We know that for any x value, for all x value, your f prime of x has to be strictly greater than 0. It cannot be 0. So this is not possible. Okay, so this is a contradiction. Not possible. So f has only one 0. All right, that completes the proof. Let's move on. Okay, the next example I want to go is this example. Use Rolle's theorem to show that there must exist some value C in the interval -2, 5, at which the function f of x is equal to x squared minus 3x minus 10 has a horizontal tangent line. Okay, then use f to find such a value C algebraically. Okay, let's worry about this one later. So how do you show that there exists a point C in this interval at which this function has a horizontal tangent line? What do you mean by having a horizontal tangent line at x is equal to C? At x is equal to C, what do you mean by having a horizontal tangent line? Perhaps I'll write horizontal tangent. At x is equal to C means f prime of C has to be 0, right? That's what we mean by horizontal tangent line. F prime of C is nothing but the slope, right? Slope has to be 0 at that point. Okay, that's when we say that we have a horizontal tangent line. So we are asked to prove that this graph has a horizon, there exists a point C such that my function f of x has a horizontal tangent line at x is equal to C. Okay, so how do you show that? So let me write what I have to show. Want to show that there exists C in the interval -2, 5 such that f prime of C is equal to 0. F prime of C is equal to 0 means I have a horizontal tangent to my f of x at x is equal to C. Okay, I want to show the existence of a C such that f prime of C is equal to 0. How do you show that? Well, this is a straightforward application of the Rolle's theorem. Okay, let's observe a few things here. Notice that first of all, f of -2 is equal to -2 squared minus 3 times -2 minus 10. This is equal to 0. That's clear. Similarly, you can justify that f of 5 is equal to 0. So looks like part of the hypothesis of the Rolle's theorem is satisfied. F of -2 is equal to 0. F of 5 is also equal to 0. And notice that I told you that polynomials are differentiable, are continuous and differentiable everywhere. Okay, polynomials are continuous and differentiable everywhere. So we have the fact that f is continuous on the closed interval -2, 5 and differentiable on the open interval -2, 5. Of course, it's differentiable everywhere, but for the Rollers to apply the Rollers theorem, this is what all I need. Okay, so I can apply the Rollers theorem. Now by Rollers theorem, there exists some C between -2 and 5, strictly between -2 and 5, such that f prime of C is equal to 0. Okay, so that means my function f of x has a horizontal asymptote or horizontal tangent at x is equal to C. That completes the example. Okay, pardon me, we have one more part. Okay, then use f to find such a value C algebraically. Okay, we need to find this value C algebraically. How do you find this value C? We need to find the value C such that f prime of C is equal to 0. So let me compute f prime of x. Here is my f prime of x. 2x minus 3. So what do I want? I want f prime of C to be equal to 0. I want to find my value C such that f prime of C is equal to 0. Okay. So how do I find such a value? Well, I'm plugging x is equal to C in my derivative function, f prime of x. So f prime of C would be 2c minus 3 is equal to 0. This will give you C is equal to 3 over 2. This is the value of C that we are looking at. Okay. All right, let's move on. Okay, the next example I want to work on is this particular example. The function f of x is equal to x times x minus 1 times x minus 3 is a cubic polynomial with one local maximum and one local minimum. We are given that this has a local maximum, one local maximum and one local minimum. Use Rolle's theorem to identify intervals on which these extrema exist. Okay. Then use derivatives to find the exact locations of these extrema. How do you use Rolle's theorem to identify intervals on which these maxima and minima are occurring? Well, first of all, notice that this is nothing but a polynomial. If you FOIL this one, you will get something like this, which is clearly a polynomial. Okay, and we know that polynomials are continuous and differentiable everywhere. Okay, that is a fact that you can use everywhere in this section. Polynomials are continuous and differentiable everywhere. Now also notice that the zeros of this function would be zeros of f of x are zeros of f. Usually we write zeros of f, okay? Are x is equal to 0, x is equal to 1, and x is equal to 3. Those are the zeros of this function. You basically set these linear factors to 0, right? To find zeros. So you get x is equal to 0, x is equal to 1, and x is equal to 3. So what this tells you is that f of 0 is equal to 0, f of 1 is equal to 0, f of 3 is equal to 0. That's what it tells you, okay? Now, notice that now I can apply the Rolle's theorem for the interval 0, 1. For the interval 0, 1, I can apply the Rolle's theorem. Because I know that f of 0 is 0, f of 1 is also 0. And also I know that f is continuous on the closed interval 0, 1 and differentiable on the open interval 0, 1 because it's the polynomial. So by Roller's theorem, there exists some C value. I'll call that C1, okay? Instead of C, I'll write C1. Between 0 and 1, there exists some C1 between 0 and 1 such that f of C1 is equal to 0. Okay, that's the conclusion of the Roller's theorem because I have f of 0 is equal to 0, f of 1 is equal to 0. My f is continuous on the closed interval, differentiable on the open interval. So I must have C1 in this interval such that f of C1 is equal to 0. Okay. Similarly, I'm not going to write the detail. Similarly, if we apply the Roller's theorem to this interval, 1, 3, this time to the interval 1, 3. Applying the Roller's theorem, there exists C2, this time between 1 and 3, such that f of C2 is equal to 0. Oh, pardon me, this is f prime, okay? F prime of C2, here it should be f prime of C1 is equal to 0, and here it is f prime of C2 is equal to 0. That's the conclusion of the Roller's theorem. It's not the f prime of C1 is equal to 0. Here f prime of C2 is equal to 0, where C2 is between 1 and 3. Okay, all right. So that's what we get. Notice that these two are C1 and C2 are critical points because f prime of C1 is equal to 0 and f prime of C2 is equal to 0. Clearly, C1 and C2 are critical points. Okay, but from a previous theorem, we know that local maxima, local extrema are critical points. Okay, those two local extrema that they are talking about in this example, we are given that we have a local maximum and local minimum. They could be corresponding to these two critical points. But we don't know yet because if you have a critical point, it does not mean that it is corresponding to a local extrema. But we know that local extrema, if you have a local extrema, they are critical points. Okay. If you have a local extremum, it is a critical point. But if you have a critical point, it doesn't mean that it's a local extrema. Okay. So what I'm going to do now is that I'm going to show that these two are the only two possible critical points. Then those two local extrema should be corresponding to this C1 and C2. Okay. All right, let's prove that those two are the only two possible critical points for our function. Okay. For that, what I'm going to do is I'm going to find the critical points of my function. Notice that this function is continuous and differentiable everywhere. So to find critical points, I'm going to set my derivative to 0. Okay, critical points are the points where my derivative is 0. Okay, we cannot have a critical point C such that f prime of C does not exist in this case because I know that polynomials are differentiable everywhere. Okay, so to find critical points, I'm setting my f prime of x to 0. That means 3x squared minus 8x plus 3 is equal to 0. This is a quadratic equation, of course. You can solve this quadratic equation using the quadratic formula. You will get these 2 points. 4 plus square root of 7 over 3. The other solution is 4 minus square root of 7 over 3. These are the 2 points, 2 critical points, and you have only 2 critical points. This is a quadratic equation. So you can have only 2 solutions there. These are the 2 distinct solutions that you get. You have exactly 2 critical points. And here, by the Rolle's theorem, we found two critical points, one critical point in this interval, the other, pardon me, in this interval 0, 1, the other critical point in the interval 1, 3. And since we are given that we have a local maximum and a local minimum for this function, and we know that local extrema are critical points, these two, this maximum and minimum, should be corresponding to these 2 points, C1 and C2. Okay, so one is in this interval 0, 1. The other critical point is in this interval 1, 3. But we don't know which one is in which. We don't know whether the maximum is in this one or the minimum in this one. But all we know is we have one of them here, one of them here. Okay, one local extrema here, the other local extrema should be here. All right, that completes that example. Let's move on. Okay, the next thing I want to talk about is the mean value theorem. Here is the statement for the mean value theorem. If f is continuous on a comma b and differentiable on, pardon me, if f is continuous on the closed interval a comma b and differentiable on the open interval a comma b, then there exists at least one value c in the interval, in the open interval a comma b, such that f prime of c is equal to f of b minus f of a divided by b minus a. Okay, here is the geometric idea of what this says. Suppose you have a graph of a function like this. This is the graph of y is equal to f of x. And say your a is here, that means your f of a here, your b is here. Say your b is here, your f of b should be here. Okay. Suppose that this function is continuous on the closed interval a comma b and differentiable on the open interval a comma b. Then what does the conclusion of mean value theorem say? You should be able to find the value c in the open interval a comma b such that f prime of c is equal to this quantity. Okay, let's look at this quantity. Okay, what is this quantity? F of b minus f of a divided by b minus a. That is the slope of the secant line joining these 2 points. If you join these 2 points, slope of the secant line is this quantity, f of b minus f of a divided by b minus a. Okay, so the mean value theorem tells you that you should be able to find a c somewhere in this interval such that f prime of c is same as the slope of this line. Can you find such a c? By the way, f prime of c means the slope of the tangent to f of x at x is equal to c. The idea is that I draw a tangent to my f of x which is parallel to this line. Can I draw a tangent which is parallel to this secant line? Of course, yes. If I draw a tangent to somewhere here, as you can see, that tangent is parallel to that red line, right? That secant line. That means if I take this point as my point C, f prime of C, which is the slope of this line, is equal to the slope of this line, which is f of b minus f of a divided by b minus a. Okay, so I'm going to draw my tangent here, which is tangent to the secant line. Okay, now I'm going to take this point to be my C. Then clearly my f prime of C is equal to the slope of this line. The slope of the secant line is nothing but f of b minus f of a divided by b minus a. Okay, so that's the geometric idea. By the way, I'm not going to prove the mean value theorem. This is a straightforward application of the Rollers theorem. Okay, I would encourage you to read the theorem. It's so straightforward. Okay, next I want to work on an example. Here is the example, last example that I want to work on. Use mean value theorem to show that there is some value c between 0 and 2 at which the tangent line to f of x is equal to x squared minus 2 has slope 2. Then use f to find such value c algebraically. Okay, so this is a very straightforward application of the mean value theorem. Let's apply the mean value theorem. Okay, first of all, notice that f is continuous on 0, 2 closed interval and differentiable on the open interval 0, 2. That's clear because this is a polynomial. So I can apply the mean value theorem. By mean value theorem, there exists c in the interval, in the open interval 0, 2, such that f prime of c is equal to f of 2 minus f of 0 divided by 2 minus 0. Okay, so that means f prime of c is equal to f of 2. To find f of 2, you plug in 2 here. You get 4 minus 2 minus f of 0 is minus 2 divided by 2. Here you get, in the top you get 4 divided by 2, which is 2. That's what we asked to prove, right? We asked to show that there is some value c between 0 and 2 at which the tangent to my f of x has a slope 2. As you can see here, f prime of c is equal to 2. Okay, c is between 0 and 2. C is between 0 and 2. F prime of c is equal to 2. That means the slope of the tangent at x is equal to 2 is equal to, pardon me, slope of the tangent at x is equal to c is equal to 2. Okay, that's what we are asked to prove. Okay, now the next step, how do you find this value c algebraically? Well, you use the algebra, you find the derivative first. Your f prime of x, x is equal to 2x. By looking at the function, you can say that you can take the derivative of this function. F prime of x is 2x. Now I solve this equation. I want my value c such that f prime of c is equal to 2. So f prime of c is 2c. You plug in x is equal to c in this function, in the derivative function. You get this is equal to 2, c is equal to 1. You get the value of c to be 1. All right, that completes that example. With that, we conclude the section 3.1. I will stop there and I'll see you next time.